This is our fourth lab, in which we analyzed the video of a weight that is dropped and attached to a spring. We analyzed the motion of the weight, knowing only the mass, which was 0.402 kilograms, and having a scale to know the distance that the weight travels, which was the length of the spring in equilibrium, which was 0.7 meters. And with that, we were able to calculate the spring constant and the spring's relaxed length. By then using a computer model, I was able to prove that the energy principle is upheld in this video, and that delta E is 0. These are the equations that I use. I will go into more detail on how I use them later. First, I started by putting in the initial conditions to my computer code, such as the mass, the starting position, and the starting velocity and gravity. I then had to find K, the spring constant. I found this by using Tracker. After tracking the motion of the weight, I used the plot on the right-hand side to find the length of the period, which I found to be about 1.59 seconds. I then used the equation T equals 2 pi times the square root of the mass divided by K. I then put that into VPython. Then we know that in equilibrium, the length of the spring is 0.7 meters. This means that the force due to gravity is the same as the force from the spring. So by setting those equal to each other, we can find that L naught is equal to 0.1194 meters. The next couple of lines were given to us by the professor down here. I then found the force due to gravity, which is mass times gravity, the force of the spring, which is equal to K times the length of the spring, the length that the spring is stretched, and F net, which is those two added together. By using F net times delta T divided by the mass plus the initial velocity, that's the new velocity, and the position is equal to velocity times delta T plus the initial position. I was able to track the motion of the weight. When I run this code, the data from the tracker is plotted along with the code. When this is run, you can compare how accurate it is. As you can tell, it starts off well, but deviates later. I will discuss this later, but by comparing these two, we can see that it's a fairly close model, and that it's a decent model for its motion. The first what does it mean question is whether or not the energy principle is upheld. There are several lines of code that I did not discuss earlier. In this section, I plugged in the equation for kinetic energy, the gravitational potential energy, and the spring potential energy. In this section down here, I found the difference in potential and the difference in these individual energies between each delta T. In this line right here, I graphed each individual energy and the change in total energy with respect to T. When I run this code, you can see the delta E, which is the yellow line, is constant. This is because while the three individual energies oscillate, the total change in energy is 0. This is consistent with the energy principle, which states that the energy within a system is constant. Now, this isn't completely true in our observed data because we didn't take into account the air resistance or the damping effect. But those aren't as important when we're looking at a model like this. The second question is about the difference in periods in the x direction and the y direction. This has to do with damping and air resistance. Essentially, damping is the equivalent of air resistance for a spring. This means that because the magnitude of the oscillation of the x-axis is longer than that of the y-axis, there's more of this effect in that direction. This means that it takes longer for it to get back to the middle, and therefore the period is slightly longer. Two respective periods that I got. In this lab, we studied the movement of a spring in 2 dimensions. By using Tracker, we were able to calculate a spring constant of 6.875 newtons per meter. Then by using a computer model, which predicted the motion of the spring, we were able to show that the energy principle is upheld in this experiment. Thank you.